This started recording. Okay, perfect.
Okay, welcome everybody. I'm just going to share my screen here so you can see my slides. There we go. Welcome to our session today called Heat Pumps for Cold Climates. There we go. My name is Trevor Trainer. I am the president of Boating Building Science, member of the Thessalon First Nation. I established Boating Building Science in 2021 to focus my consulting practice on Indigenous housing issues. Since then, I've done a lot of work in extremely cold climates, doing a lot of work in Nunavut in the Arctic right now mostly on the performance of building enclosures, but also learning a lot and getting into more of the mechanical systems and a little bit about what we're talking about today, which is heat pumps. I've also had the experience of switching over my own house here in Ontario from a natural gas furnace to a heat pump system. So I've got that experience too that I can share as we go. So we've been hearing quite a bit in some circles about heat pumps. And I just wanted to kind of break down, first of all, what is a heat pump and how they might be a good tool for us to use. So what is a heat pump? A heat pump is a mechanical system designed to move heat from one area to another area. So it's not generating its own heat, but it's gathering heat from the environment. Let's make sure we're all on mute so that we have a nice quiet background. And so the heat pump uses something called the refrigeration cycle. Even when it creates heat, we still call it the refrigeration cycle. There's a few key components to that system. The first one is the expansion valve. The expansion valve relieves pressure in this system and passes the refrigerant into this evaporator coil. And it does so as it releases it as a cold, low pressure liquid. The refrigerant then goes through the evaporator coil and warms up as it's going through the coil and picking up heat from the environment, from the air around it with the help of some fans, and ends up going into the compressor. In the compressor, this cool gas now, it starts off as a liquid, becomes gasified as it gets warmed up. This cool gas gets compressed, and so the heat that's in it gets compressed into a smaller volume and fed into the condenser coil. And on the condenser coil, a fan is used to blow across and steal the heat from that warm gas, turning it back into a liquid and keeping that cycle going. So it's not super important that we understand every step of this, but it is important to understand that we're gathering heat from the environment and moving it to another place with using heat pump technology, using this cycle, which we call the refrigeration cycle. The other part of this that's a little bit technical is what this fluid is that's moving through here, what we call the refrigerant. So what is a refrigerant? It's a fluid. So a fluid is something that could be a liquid or a gas, depending on the temperature it's at and the pressure it's at. And refrigerant is a fluid that's used to move heat from one area to another in the refrigeration cycle. Refrigerant is a material that's suitable for moving large amounts of heat in a small volume. So we can't just use water, and we can't just use air. We need to use some special materials or fluids that are good at storing large amounts of heat in a small volume. A refrigerant has to have some really special characteristics. It has to have a relatively high critical temperature, so it can become really hot without becoming volatile. It has to have a low freezing temperature. It has to have a high latent heat of vaporization, meaning it can hold a lot of heat before it evaporates. It has to have low condensing pressures, so we don't need to put a lot of pressure in it to make it condense. And it has to have a low oil and water solubility so that it can function in this machine that we're putting it in and still work properly. And also it has to be like a reasonable cost, right? We can't have material that's excessively expensive. So in the early days when refrigeration was first invented, the refrigerant that was used was actually a very toxic and flammable material. They started off using ammonia, and then sulfur dioxide was also used. So these are really volatile and flammable materials, and it wouldn't be appropriate to have that type of material inside your house. So these were really just commercial applications at that time. In the early 20th century, at the turn of the century, there was an invention which generally is called Freon. And Freon was developed as a synthetic, non-flammable, and relatively safe alternative to the previous refrigerants we were using. So this was a major step forward. Now it would be safer to have a refrigerant inside of your building, inside of your home, because it's not flammable. One of the things that was discovered over pretty quickly, though, was that Freon was found to have a major and negative effect on the ozone layer of the Earth. So even though we're not purposely releasing Freon into the atmosphere, even small amounts that get released during production and manufacturing were causing a hole in the ozone layer, which was causing environmental impacts. Freon was also found to have a very high global warming potential. When we talk about global warming potential, we typically talk about CO2 emissions. Well, Freon has a global warming potential of about 3,000 times that of carbon dioxide. So although it was safe in terms of flammability, it also had pretty significant environmental issues that we had to deal with. So in 1986, Canada and a lot of other countries signed on to the Montreal Protocol, which committed them to phase out the use of Freon. So over the next 30 years and up into where we are today, refrigerant technology was further improved, and Freon was replaced with what we now call HFCs, hydrofluorocarbons. And hydrofluorocarbons are safe for the ozone layer, which was a major improvement. But they also still have pretty high global warming potential. So if they get released into the atmosphere, they have the potential to create global warming in our atmosphere. And so in 2016, we've moved forward, and the Kigali Amendment was added to the Montreal Protocol for the phasing out of the use of HFCs. And that's sort of where we currently are right now. We're in the midst of phasing out HFCs, the hydrofluorocarbons, and we're making a transition to HFOs, which is hydrofluoroolefines, I think it is. And the big difference between HFCs and HFOs is that HFOs are safe for the ozone, and they also have very low global warming potential. So we've made major improvements there from an environmental perspective, and from a performance perspective too. These chemicals are being custom made to work in the new systems that we have. So that's the history of refrigerants and how, in our current state, we're now transitioning to much safer and more environmentally friendly refrigerants. So heat pumps aren't all that crazy. They're not all that complicated in that we have them in our homes already. Our refrigerators and our freezers, all right, have heat pump systems in them. The difference being we're using that heat pump to cool the inside of our refrigerator. At the same time, whether you notice or not, we're actually sending heat into our homes through the back of the refrigerator. And that's the same process we're going to use going forward as we look to use this system to heat our homes. Similarly, if you have an air conditioner, whether it's central air or a window air conditioner, this unit also has a heat pump inside of it. And in this case, it's rejecting the heat to the outdoors and collecting heat from the indoors. And so that heat that it's producing doesn't end up inside of our homes. In this case, it ends up being rejected to the outside. Well, when it comes to heat pumps to heat our homes, we're just going to basically take that same cycle and we're going to reverse it and add a lot more technology to it. So using a heat pump to heat our homes, when the right conditions exist outside, and we'll talk about what those are, we're able to use this refrigerant cycle and this technology to pump heat from outside into our homes to keep our homes warm. Even in cold climates, there's a certain amount of heat energy in the air outside. The absolute zero is, I think, minus 300 in some degrees Celsius. Anything above that, there will be a certain amount of heat energy in the air. And we've been developing the technology in these heat pumps to gather that heat, compress it, and move it into our homes. And so heat pumps can be a very energy efficient way to provide heat to our homes. We'll talk about what circumstances they'll work, and what circumstances they work best, and when they might not be the best solution. We'll talk about both sides of that. When we talk about heat pumps, there's different ways in which the energy efficiency is rated. One is called SEER, or the Seasonal Energy Efficiency Ratio. That's usually used on the air conditioning side, on the cooling side, and it's used to rate cooling systems by summing the total amount of cooling provided during the cooling season divided by the total electrical consumption. And so when it comes to air conditioners, SEER 18 or above would be considered good performance for a typical air conditioner. Modern heat pumps can actually air condition at SEER levels at 25 up to, I think, SEER 30. So really high efficiency because of the technology that goes into those. The other sort of flip side of that is the heating season performance factor, the HSPF. And it's used to rate the heating system by, again, summing the total amount of heat provided during the heating season and dividing by the total electrical consumption of that unit. And when it comes to HSPF, an HSPF of 9 is considered good performance for a heat pump system. So those numbers are kind of like something to keep in mind, but they're hard to kind of wrap your head around a little bit in terms of efficiency. The easiest way to talk about the efficiency that I think is the coefficient of performance, or COP. And that's basically the ratio of heat energy delivered into an indoor space compared to the amount of energy used by the system. And that might change as conditions change, but COP is easy to understand because it's basically a way to compare it to, let's say, an electric baseboard heater, which would have a COP of 1 unit of energy in, 1 unit of heat out. When it comes to heat pumps, we can get coefficient of performances between 2.5 and 4. So 2.5 times to 4 times more efficient than an electric baseboard heater, depending on the conditions. And we'll talk about what some of those conditions are. We're going to talk about some different types of heat pump systems. We'll talk a little bit about ground source heat pumps, but mostly we're going to talk about air source because the affordability and access is much higher for air source. We'll talk about central air source heat pumps, ductless air source heat pumps, and also a relatively new in North America technology, the air to water heat pumps. So first, let's talk about ground source heat pumps. So ground source heat pumps use the earth as the heat source for that refrigeration cycle. Instead of trying to pull heat out of the air, it pulls heat out of the ground. And there's some real big benefits to that. If we look at this chart, you can see these two lines show the ambient air temperature over the course of a year. So, minus 10, minus 15 in the winter, above 15, 20 in the summer. And so the air temperature is changing quite a bit. But what these other lines show us is what's happening below the ground, depending on what depth we're going. If we look at, let's say, the pink line, that's the temperature of the Earth 5 meters below ground. And you can see whether it's summer or winter, there's very little change in that temperature. And so when we're trying to use a heat pump to either grab heat out of that in the winter or reject heat in the summer to that, we have a really steady source that we can use. So ground source heat pumps can really be very efficient because they've always got that steady state of the ground temperature to work with. Some of the negatives of ground source heat pumps is they require long runs of coolant piping, either buried down below the frost line or in deep wells that are, drilled into the earth. Ground source heat pumps, they create a warm coolant or water, but it's usually some type of coolant system that can be distributed to radiant heating or cooling systems inside your home. Or it could be run through a forced air system using a heat exchanger. These systems are really expensive to install, mostly because of the excavation or well drilling that's required. But they can achieve really high coefficient of performance, and they're much less affected by the outdoor air temperature, which, depending on where you live, could be an issue that you have to deal with. And we'll talk more about how air source heat pumps work differently because of they're reliant on the air temperature. Also, when we're talking about ground source heat pumps, though, the type of soil and the moisture content of the soil really matters for heat transfer. And so depending on the conditions in your community, it may be a good approach or it may not be the best approach if you have really dry soils or obviously bedrock close to the surface. Mostly what we're going to talk about today is air source heat pumps. So air source heat pumps, I forgot to change that. Instead of using the earth as the heat source for the heat exchange, they use the air outside. And they use that same cycle. You'll have an indoor unit and an outdoor unit, and then your compressor and your expansion valve in the system. There's two types generally of air source heat pumps. There's the standard air source heat pump, which have been around a lot longer. A standard air source heat pump can provide air conditioning year round and can provide heating down to about minus 10 degrees Celsius. So relatively limited to where these can be used in Canada because of that limitation. After minus 10, typically they aren't able to provide any heating energy and a backup source is needed. Cold climate air source heat pumps, however, are designed to efficiently heat homes in temperatures well below minus 10, more down to like minus 25 or minus 30. Because of some advanced features they have, including variable speed compressors, intelligent defrosting cycles that they have built in, and improved insulation in the system to allow them to work better at lower temperatures. So they can operate at outdoor temperatures as low as minus 30, and they can provide both heating and cooling year-round, potentially, depending on your climate. The one thing about air source heat pumps, though, is that as the outdoor air temperature gets lower, their capacity starts to decrease. And so when we design a system that's going to be used to heat your home, we have to keep that in mind. So if we look at this table here, this chart shows the heat loss that's happening through the walls and roof and foundation of your home at different temperatures. So as we get colder from plus 20 to minus 20, the heat loss goes up, and at minus 30, you can see in this example how much heat loss there is through the walls and roof of your house. Let's say in this example, about 38,000 BTUs. So as the temperature gets colder, heat loss goes up, and we need more heat to maintain our temperatures, indoor temperatures. If we were to look at a gas or propane furnace, it doesn't matter what the outdoor temperature is. It always kicks out a certain amount of heat And so in this case, let's say it's 48,000 BTUs. And so the heat loss and the output of the furnace never cross. And so this furnace, no matter what the temperature is outside, can produce enough heat to heat your home. But that's not quite as simple when it comes to air source heat pumps. If we were to look at a standard air source heat pump, once we get below about 10 degrees Celsius, the capacity, its ability to kick off heat starts to go down and down. And once we hit about -10, it actually drops off much faster than this. And so at some point, in this case around -10, that standard air source heat pump no longer can give enough heat to your house to maintain 20 degrees Celsius. So that's a problem. So we've got this zone here where you need supplemental heat to something else to add heat to the house to top up the system. Now, fortunately, we've developed cold climate heat pumps, which work a lot better and drop off at much slower rate. So in this example, they start to drop off in their capacity around the same temperature, but they really maintain their ability a lot longer. And in this example, we don't really cross over the heat loss until about -25 in this example. So in this example, after it gets colder than -25, we're still going to need a little bit of supplemental heat into our home to maintain 20 degrees Celsius. But it's obviously a much less amount because we're using this cold climate heat pump. Now, the interesting thing about a home is that these things don't act all by themselves, right? The mechanical system and the building enclosure all interact and they act as a system. And so what would happen if we improved the building envelope in this case? If we added insulation and R value to our walls and roof and foundation, and we could reduce the outdoor temperature. We could reduce the heat loss through the home. Now that same cold climate heat pump can provide enough heat for the whole house until almost -30 degrees. So this is the approach that I took at my house when I did my renovations. I knew I wanted to switch over to heat pumps for various reasons, and we'll talk more about that as we go. But I also knew that my house was very poorly insulated and it needed to be improved. And so before I installed my heat pumps, I increased the insulation levels in my attic, in my walls, and in my basement and my foundation. And so now this is more of the condition I've got where I've improved my building envelope, and now a cold climate heat pump can provide 100% of the heat I need in my climate here in Southern Ontario. And so the other thing that changes as the outdoor temperature gets colder is the efficiency of the air source heat pump. So again, a furnace, if it's natural gas or propane or oil, it doesn't matter what the outdoor temperature is really. It always operates at, let's say, in this case, 94% efficiency, okay? Electric baseboards, on the other hand, will run, no matter what the outdoor temperature is, will run at about 100% of efficiency. You think, well, how can you do better than 100% efficiency? Well, actually, heat pumps are really good at that. And so now I have to change my scale when I start looking at a ground source heat pump. So now instead of talking about efficiencies, we're talking about coefficient of performance. Whereas the baseboards and the furnace acted with a coefficient of performance around 1, a ground source heat pump can have a coefficient of performance of 3.5, 3.75. And because it's below ground, it's not really affected by the outdoor temperature. So it can maintain that no matter what the outdoor temperature is. Again, that's for the ground source heat pump. When we start to look at air source heat pumps, though, there's some limitations. That standard air source heat pump starts to drop off in its performance quite quickly once we get below about 10 degrees. To the point where by the time we're at -15, it's at about 1 to 1.5 coefficient of performance. So it's not nearly as efficient at -15 as it was at 5 or 10 degrees. The cold climate heat pump, though, performs a lot better and drops off a lot more slowly. So even at -15, it still has a coefficient of performance of about 2.5. So it's still 2.5 times more efficient than electric baseboards at -15. Once we get down to about -25, it'll still be about coefficient performance of about 1.5. So still 50% better. And so you can see that depending on how many hours of the year you have below -20 or below -25, that the use of a cold climate air source heat pump can still save a lot of energy compared to using a furnace or electric baseboards to heat your home. So let's say now just talk about different types of air source heat pumps, and not in terms of whether they're cold climate or warm climate, but what do we do with that heat inside the home? So the first one is central heat pump system. And basically in a central heat pump system, it's like a furnace in that there's a central heat exchanger and an air handling system that then takes and pumps that warm air that it's creating in the heat exchanger to different areas of your home and spreads that around. So just like it would in a regular forced air furnace. You wouldn't really notice if you're living in the home any real difference. There are a few subtle differences in that the temperature that's of the air that's being supplied is a bit lower. So we need a bit more volume of flow to give us the heat to the different areas of the house. So you might notice that, but probably not. If you were replacing a furnace with a central air source heat pump, you may be able to use the existing ductwork, but that will have to be checked by a mechanical designer, because depending on the flows, you might need extra airflow, which might mean you might need to update or upgrade or upsize your ductwork a little bit. And so because that lower supply air temperature requires a bit more airflow to get the heat where it needs to be. So other than that, though, it's very similar to using a furnace, and you could likely do a straight swap out if you wanted to from a propane or natural gas furnace to a central heat pump system. The other option, this is the one I chose to do in my house, was to abandon my ductwork. I wanted to take out a wall in my main floor that fed most of the ductwork upstairs. So I didn't want to use ductwork anymore, and I went to a ductless heat pump system. In the ductless heat pump system, there's one outdoor unit that does the exterior heat exchange. And then there's multiple heads inside that provide heat or cooling in the summer to the interior of the home. And this can be between it can be between 1 and 4, I believe. There may even be 5 that you can hook up to one outdoor unit. And basically now you have these point sources of heating or cooling. And you have to be careful and strategic about where you put those in your home, so you don't end up with cold rooms. I know for my house, because I upgraded the insulation in my home, I just have one of these units on each floor. So I have a central point of heating and cooling on each floor, and it really hasn't been a problem in terms of having any cold rooms in my house. I do have a small compact house, about 500 square feet per floor, basement, main floor, and second story. But it's worked out pretty well. The other big benefit that I've found from using the ductless mini split is now I can run different temperatures in different zones of my house. So right now I'm in my basement. You can see this is the indoor unit for my whole basement right here. When I'm not here, when I'm not working on the weekends or in the evenings, I can turn the temperature way down in here. And when I'm here, I can easily zone up just this area that I'm in. In the upstairs where all our bedrooms are, we like it cooler up there, and it's easy to set that to be cooler the second floor to be cooler than the main floor because they've each got their own thermostat. They each have their own controllers. So it's really convenient that way, and it's good for energy use also. The third type I wanted to quickly talk about was the air-to-water heat pump system. In the air-to-water heat pump system, you still have that outdoor unit that's grabbing heat out of the air. And then instead of compressing it and putting it into the air indoors, it puts it into water inside typically a water tank. And you can use that water either for showers and just domestic hot water. You can also run it through radiators or a heated floor system to heat your home.
Okay. Okay. Bye.
Can we just make sure we're all on mute? So
I
that
evicted you. You owe money. You should try.
Thank you. So yeah, this system can be used for hot water and heating the home potentially. So it's not as common. These are relatively new in Canada, much more popular in Europe, but they are starting to become a more realistic option in Canada. And then there's also a similar air to water heat pump system that's just a heat pump water heater. The difference of this being that the compressor just sits on top of the hot water tank, and it just grabs or steals the heat out of the air in the room around it. So it's not grabbing outdoor air, it's using indoor air to heat the water. So it steals that heat from the indoor air, which does add to the overall heat load during the winter. So you have to make up for that with your heating system. But also in the summer, it actually provides basically free air conditioning to the area that it's in because it's grabbing the heat out of the air to warm that water up. The other benefit with this is because of the way it works, it's actually providing dehumidification all year round, which can be a benefit depending on whether you, especially if it's in I have one in the basement here. It tends to be higher humidity down here, and that really helps control humidity also. So just an option, and this is just an ad I stole. I don't know if it really saves $375 a year to switch, but it does save quite a bit of energy if you're going from an all electric, just an electric resistance hot water heater to an air source heat pump water heater. Yeah, I can't remember why I put this here now. Let's see. Okay. Right. So what I want to talk about next is if we do decide that we're going to use this, even a cold climate heat pump or even a standard heat pump, how do we make up for this difference? What are the options for supplemental heat and emergency heat too, right? If you have an extended period of time with no electricity, what are our options? So we have a few options. Supplemental heat may be required to just top up the heat in your home during the coldest parts of the year, depending on your climate, depending on that heat pump sizing. If the heat pump's been oversized enough, you may not need it, but it does get expensive to oversize when it comes to heat pumps. So really right sizing it makes sense. And of course, depending on how well insulated your home is, can really affect how much supplemental heat you may have. Also, it's really probably a good idea to have just a backup source of heat for power outages or during mechanical breakdowns. And the key for that is if you have a backup heat source, it can't be electrically run either. If the idea is that when the power is out, you want some heat. So what are some options? Supplemental only. So if you're just looking to supplement, you've got lots of options. You could use electric baseboards to supplement that heat on the coldest days. You could use an electric resistance coil in your air handler. So if you have a central system, a lot of times these are built with an electric resistance coil in the air handler that's just there to top it up when needed. And you wouldn't even notice that as living in a home. You could also use something like a pellet stove. Again, kind of supplemental only. Pellet stoves require some power to run the auger. although I think some people can run those off of a pretty small battery as a backup. So maybe it could also be a backup. But if you're looking for something that for heat when the power is out, then you're a little bit more limited. Obviously, a wood stove is always a safe backup in terms of if you have wood available, you've got an emergency source of heat there. Gas heater or gas fireplace. So this is what I have in my house. I just have a couple of gas fireplaces that I use just primarily for the ambiance of them because I like the way they look, but also they can give off a significant amount of heat in a power outage, and they'll run with no electricity. They just have little battery powered starters. That's all they need. The other option we'll talk a bit more about is the dual fuel furnace. And we'll get into a bit more detail what that looks like. So if you are using a central heat pump system, remember that heat pump system, there's the outdoor unit, the indoor unit, that indoor heat exchanger lives inside this air handler. And you can also add an additional source of heat in this air handling system. So again, it could be electric resistance, like we talked about, which could be good for supplemental, but not good for backup in a power outage. This could also be a hydronic heat exchanger using hot water from your hot water system to exchange heat, or a dual fuel system. So these come as packages, and the dual fuel means that there's actually burners up here that can burn natural gas or propane to supplement the heat that's coming out of your heat pump heat exchanger. And so in these systems, the dual fuel systems specifically, there's a lot of control issues. It's a pretty complicated system because the system has to know when to fire up these burners. So there has to be a lot of sensors and a lot of automatic controls involved. But basically, it's a combination of a central heat pump and a forced air furnace. It utilizes one central air handling system. In a power outage, you could use the forced air furnace aspect of it, but you would need some type of power source to run the furnace fan. That can typically be done with a small generator or potentially with a battery backup. Again, this is a pretty complex system, so it needs special design and special control strategies need to be used. And so you really need to get an experienced mechanical designer to come in and design this, and an experienced contractor to install this type of system. But it is available to kind of get the best of both worlds in terms of using the heat pump when the outdoor conditions allow, and then supplementing that with some natural gas or propane use when the temperatures start to really drop and get out of the range of your heat pump system. So a couple things you need to understand or think about if you are considering making the switch, especially if you're heating currently with fossil fuels, with propane, natural gas, or diesel. The one is, do you have enough electricity supply to your house? If you're currently heating with electric baseboards, you definitely do have enough electricity. That's not going to be a problem. But if you currently heat with oil, propane, or natural gas, you'll probably have to check with an electrician to see if the supply into your house is large enough, so the service into your home, and also if you have enough room on your electrical panel. And then just to note, a cold climate heat pump needs two 40 amp breakers in the panel. So you need to have enough room for that in your panel, and you need to have enough supply to your building to run that. And working with an electrical designer or an electrician can help you determine that. So why would you choose a heat pump over just working with what you've got, your natural gas furnace or your propane furnace? One is saving energy. So this is one of the reasons I did it, was to save energy. Remember, the best you're going to get out of a furnace is about 94 to 96% efficiency. Electric baseboards are about 100% efficiency, whereas our heat pumps run somewhere between 1.5 and 3.5 times more than that. So up to 350% efficiency. So the overall energy use required for heating your home could be reduced by 50 to 70%, depending on your climate and where these curves spend most of their time. So that's a really significant savings in energy. But it's not just that you're saving energy, it's the type of energy you're using. And that brings us to number 2, is reducing your carbon footprint, the operating carbon of your building. So depending on your heat pump choice, your existing system, and your power grid content, changing heating systems to an air source heat pump or a geothermal could reduce operating carbon by 95% or more. And here's why. If we look at, first of all, what the CO2 content or density of our fuels are, natural gas is at about 70 grams of CO2 per megajoule, propane's at about 75, and heating oil is at about 95 grams of CO2 per megajoule. Now let's compare that to electricity. Well, the problem with electricity is it really depends on where you live. If you live in Manitoba, if you're on the Manitoba grid is at an intensity of about 2 grams of CO2 per megajoule. So it's way, way less. So is Quebec. Ontario, where I am, we're at about 20. So that's still a significant improvement over what burning fossil fuels would be from a carbon perspective. Once we get into Newfoundland, Yukon, Northwest Territories, and all of these, actually the carbon content of the electrical grid is such that changing from burning natural gas or propane on site to electricity would mean you actually increased your carbon footprint. So it's really important to know, if that's the goal of changing over, what the carbon intensity of your grid is. And here's some examples. So for example, I do a lot of work in Nunavut, where the electricity is almost 100% generated by diesel generators. So at almost 800, so more than 10 times the carbon density the electricity has over burning the heating oil. And so what we end up doing in Nunavut is sticking with our boilers that run off of heating oil or diesel, both because there's not enough electricity to run a heat pump. It's too cold to run a heat pump for a lot of the year. And also we'd use more carbon if we did that. So understanding your electricity grid is also an important part of this. Why choose a heat pump? Potentially for saving heating costs. This one's a little harder too. It's very regional, your energy costs. So depending on your heat pump choice, your existing system, existing fuel pricing, and local electrical pricing, changing a heat pump could save money. It could also cost you more money. I'm still looking at my bills from 2 winters ago to last winter and this winter. I'm about breaking even on cost, because although I'm using about 1/3 of the amount of energy to heat my home that I used to, the cost of that energy is about 3 times the amount. So electricity here in Ontario is about 3 times more expensive than natural gas. So I'm saving a lot of energy right now, and I'm saving my carbon emissions, but I'm not saving any heating energy or costs at this point. I'm basically breaking even. So again, depending on where you are and what the prices are, you could save a significant amount of energy, especially if you're currently running electric baseboards. You're going to automatically save 50 to 70% in costs. If it's propane or natural gas, it really depends on the pricing of both the electricity and your fuel. Why choose a heat pump? One of the reasons is if you currently don't have air conditioning, and with climate change making our summers hotter, longer, and more humid, when you switch over to heat your house with a heat pump system, you also get the air conditioning aspect of that comes with it. So no additional equipment needs to be installed to provide cooling and dehumidification during the winter months. So that's a really big bonus. If you're thinking about adding air conditioning to a central system, the cost of that compared to the cost of switching over to a heat pump heating and cooling, the difference between those two might not be that much, and it might be worth making the switch for both your cooling and heating needs to an air source heat pump. Why might you not want to choose a heat pump, specifically an air source heat pump? One would be the climate factors. If your outdoor temperature spends a significant amount of time below 25 degrees, then you're going to need a significant amount of supplemental heat. And your heat pump's going to be running in lower efficiencies for more of the winter. You'll still save energy because a lot of the energy you use in the shoulder seasons when it's not as cold out, you're going to save a lot there. But you will need to have that supplemental heat source, which is going to use more energy, and it's going to start to balance out a bit. So at some point, the upfront cost of the heat pump and the supplemental heat may not be justified if you live somewhere where there's weeks and weeks on end of temperature below 25 degrees or minus 25 degrees. Secondly, your electrical grid factors, right? So we looked at those electrical grid emissions factors. So if you live in a community with an unreliable electrical grid, then other heating sources might be a safer choice. If you live in a community with a small local grid like they have in Nunavut, there may not be enough grid capacity to switch from burning oil and gas in a furnace to electricity for home heating. And the carbon effects of that might be significant. You might be making a worse choice from carbon emissions. And then also, if the service to your house or the size of your panel is insufficient, then these are going to need to be upgraded before you can make the switch to an air source heat pump. And obviously there's a cost to that, and that all has to be factored into the cost benefit analysis of that. Right, electricity source and costs obviously are really key. As I said before, some electrical grids are very low carbon in Canada, some are very high. We need to keep that in mind. And also just the cost of electricity. If the cost of electricity is greater than 3 or more times the cost of your heating fuel, then your energy bills might go up in the short term. And so that might be a reason not to choose a heat pump. And then lastly, I think would be, do you have the technical support? And can you afford the upfront costs? So heat pumps, they are complex heating systems. You can't just take one, buy one at Home Depot and stick it in your basement. It takes a lot to install it, to set it up properly, to commission it. You need access to qualified refrigeration contractors and technicians to properly install and to properly maintain the systems. Depending on your access to contractors, the upfront installed costs can be higher than a standard boiler system or forced air system. If you're bringing in specialists from out of the community, that can be a more expensive thing to do. And then if air conditioning is a part of your HVAC package, regardless, then costing may be lower than for a forced air furnace. So if you're gonna buy a forced air furnace and an air conditioner, it actually may be cheaper to just get a heat pump system that can do both heating and cooling up front. And so that might be a good reason to do it if that's the plan. Just a little bit about pricing. So this is very regional, but I did have just switched over in the last year and a half. So I do have some sort of pricing to get you an idea. For me, my 3-headed ductless cold climate system was a 33,000 BTU system, so 2.5 tons if you're a HVAC person. And it cost about $17,000 installed. Also, I bought a 50-gallon heat pump water heater for $2,600, and I installed that myself. So just to give you some general idea of, at least in Southern Ontario, in more remote areas, these prices, especially the installation prices, might be higher depending on where you live. There are some incentive programs out there. I don't have a complete list of them. They change quite rapidly, but there is something Canada-wide called the Oil to Heat Pump Affordability Program. So that's specifically if you're running off an oil furnace right now. You could receive up to $10,000 to switch from heating oil to heat pumps if you meet these requirements. And you'll have to go deep into the websites to see if you meet all those requirements. In Ontario specifically, there's a couple of different things going on through Enbridge and a group called Save on Energy. You can get cold climate air source heat pump. You can get up to $2,000 back. There's not a lot of requirements for these. If you do heat your home with electricity, oil, propane, or wood, you can get up to $7,500 back. And there's actually some incentives to rent a heat pump, up to $2,000 back on rentals. Similarly, for ground source heat pumps, there's incentives that are even a little higher. But again, the upfront cost of the ground source heat pump is quite a bit more, maybe up to 2 or 3 times more than an air source heat pump. And then I know specifically in Nova Scotia, they actually have sort of an upgraded version of the Oil to Heat Pump Affordability Program, up to $15,000 grant to cover the costs, a bonus of $250 if you meet the requirements of the system. I'm sure there's other ones out there and other ones coming. And again, they do change all the time as we have new governments that have new budgets. These things tend to change. And so we may be seeing different ones, different incentive structures coming out in the near future. So keep an eye on that. Well, that's all I've got for now. Looks like we've got about 5 minutes for questions. If you do have a question, maybe just if you can hit the raise your hand feature, or if you want, just unmute yourself, and yeah, we can ask questions if you want. But if we don't have any questions, that's okay too. We can.
Well, we do have
Clint.
a bunch of questions in the chat.
Oh, yeah, I wasn't watching the chat.
Well, there's
Aha.
I was
No,
too
there's
busy. I was busy
there's
presenting.
Art.
Yeah,
has
Art, go
just
ahead. You got a
commented.
question.
No questions, just sharing information.
Yeah,
Oh,
good
great.
information.
Thank
Art,
you.
where are you in Manitoba, I believe?
Correct.
North, south?
Yeah. Southern, but I'm with Efficiency Manitoba, Crown Corporation, that we
Oh, yes.
we work with First Nation communities, well, all Manitobans, but I work with First Nation communities across the province, specifically on heat pumps. So thank you, Trevor, for sharing this. It's always good to kind of get a bit of a refresher. And I think one of my comments was, as anyone who's reading the chat could see,
Yes.
air source heat pumps in our colder climates, which is quite frankly most of the province, really are best for kind of dual fuel systems, where the air source heat pump, you're using it, throughout the year, and then you've got your backup or supplementary heat in the winter for those minus 25 and below. Also very good for regions where ground source is not viable, like on the Canadian Shield, where it's cost prohibitive to kind of get your ground loop through bedrock. But in the south, I mean, the ground source heat pumps are really the way to go, particularly for this cold climate, because it works very well, but larger upfront costs as well. But thanks, Trevor. This has been fantastic.
Yeah.
Art,
And Art
Art,
also
I'll just,
put-
sorry there, Claude, or Trevor. Art, you guys do fabulous work with First Nations and your colleague Ian.
Correct. Yes.
Yeah,
Ian's on
and,
the call too now, I believe. So
Yeah, I hats off to both of you. I know Ian is Mr. Beauregard, especially up in Swampy Cree and helping to get that information out. So you guys do great work, and I know First Nations appreciate that.
well, thank you for your kind words. It's much appreciated.
Go ahead, Trevor. Sorry.
No, that was me, John. So
Oh.
also Art has put a link in the chat for people, the First Nations in Manitoba. He's put a link in there to share with everyone.
Yeah.
Thank you, Art.
So, yeah,
You're welcome.
another question was, what's the actual cost to have a heat pump installed into a house? I know my estimate was like about,
There's mine, 17.
the numbers are crazy
This is my
depending,
bill.
right? Depending. Go ahead, Trevor.
Yep, this is my bill right here, 17,000.
Yeah,
That's-
mine was about 20,000.
Yeah.
Hey, this is Rudy here. I'm out in BC. You know, it cost you about $3,000, maybe $4,000 if you retail purchased a heat pump, let's say 36,000 BTU. And it takes them about a day to put it in. And I've seen costs of labor as much as $10,000 on top of that. And that it is a new way just to print money. I am so discouraged when I, do this for the First Nations out here, and I'm setting up these type of systems for them. And I'm just so discouraged at the fact that these guys are just taking advantage of the whole system. It's unfortunate. The other thing, Trevor, I was going to ask you, we do not in BC, we have industry, geez, I'm having a mind fart here. Technical Safe BC. So if you're a gas fitter, you have to get a permit. If you're an electrician, you have to get a permit. But we don't have anybody here in BC that you're required to get a permit to install a split heat pump. How is it where you are?
That's a good question.
That's a very good question.
I don't know. I know that it's really important that it's an experienced person installs this and designs it, because there's a lot going on in the installation. I worked with the installer, just like drilling holes for him and stuff, and watching, because I was really interested in what he was doing. And there's a lot to it. And so I don't know if there are like regulatory requirements or not, but regardless, make sure if you're hiring someone that they have a lot of experience installing these types of systems, and it's not they'll figure it out as they go along kind of a situation.
Well,
Art, you got any
company-
comments on that? Sorry, Art, you know? Sorry, guys.
So out here, I mean, and I agree with you, Trevor, you would want to have somebody that works for one of the, heating companies, but has a refrigeration ticket.
Yes.
That's the key
Thank
right
you.
there,
Thank
right?
you. Yeah.
Because, like you
Agreed.
said,
Yes.
there's the involvement of the gases and so on, and setting these systems up, checking for leaks and so on. And yeah, you would want to have somebody with a refrigeration ticket.
Yes.
And maybe try to negotiate with them a little bit to get your prices down, knowing that you would know. If you go on Amazon right now, you can buy a Sendville unit, 24,000 BTU delivered to your door for about $2,500. So it's not that the systems are readily available and they're not that expensive, but it's for some odd reason, like I'm belaboring this point, is that there's this need to gouge everybody for 8 hours worth of work. So we're working with our people here on the First Nations and the installers to get, better rates if we, are having 6, 7, 10 units put in, right?
Yeah, that's a good way to look at it, is to work in volume. I do know though that installing my 3-headed indoor unit here took 2 guys 3 days to do it. Like it's not just slapping it in. There's a lot of running, drilling through holes, sealing things up, running line sets. You know, there's a lot
Absolutely. Under that
to it.
kind of-
Yeah.
yeah. When you're doing multiple head systems.
Up on scaffolding. Yeah.
Yeah, absolutely. Now, another question, you didn't really bring that one up, is when your compressor is located. Where is yours located, on the east side of your building, the west side, south side? You know, because that makes a big deal too. I installed a heat pump system a couple of years ago, and I can't rave enough about them, how wonderful they are.
I love
And
mine.
mine, I made sure that I kept it out of the sunny side. I mean, I live in the desert, so.
Yeah. In my neighborhood, the houses are relatively tight together. So there's not a lot of direct sunlight that gets down to the area that I put this. And there's a fence on one side of it to block the snow. And there's this overhang of the roof above it to protect it from the snow. So I was kind of lucky that I had a good spot to do it. But that is a good point, that it needs to be held up off the ground so that the condensation and the ice that forms under it doesn't get into it, and that it's relatively protected from the sun and the wind and blowing, drifting snow. Yeah.
You know, and my house, large house, I have it on hydronic heating. And you really sparked me now when you said, because years ago I tried to look for systems to water, right? And you just couldn't find anything out there. And while you were talking, I found Arctic heat pumps, right? And I'm just waiting for an answer back from them to see what they're offering, right? What a great idea. I'm thinking that's what I'll do with my hydronic heating system, implement some of that and reduce my costs, gas costs.
Yeah. I even have a small, like a bathroom and an entryway that are tiled that I heat just off of my my heat pump water heater.
Oh yeah.
It just runs off of, that normally just supplies domestic hot water, but it heats the floor in one little area of the house.
Thanks, Trevor.
Yeah.
Yeah,
So
great,
all these things are
great.
possible.
Yeah, and I think the question that Rudy, and it's important to get a couple quotes, right? Try to get value for money. But if they're the only game in town, then I think that's where you almost have to send the quote out for review. And again, FNNBOA, we can provide that input through our Indigenous Building Knowledge Exchange. So if you're putting in heat pumps and not sure about the cost, feel free to share it with us, and we can take a look at it and give you some input of whether or not it's reasonable value.
Hi guys. Hi Trevor. I was going to kind of just kick in from the opposite side of the fence, so to speak. Obviously, I'm using a forced air furnace with gas, and probably to replace that unit, I'm talking $5,000-$6,000. If I add on AC, I'm probably looking another $3,000-$4,000. So just to kind of give people a general idea, it wouldn't be out of line to basically say, you're looking at least eight to 10,000 just for a forced air gas furnace by itself. So again, certainly I would always recommend it's installed by a licensed heating and or refrigeration contractor. So, and by the way, Trevor, I like the way that you introduced the topic. You brought it down to earth, that even I think most people kind of got what the heat pump's all about. So again, thank you for
thanks,
really,
Doug.
I think bringing that part home.
One other thing I'd like to add to this discussion is, as Trevor was indicating, a standard heat pump may work, down to about -10 Celsius efficiently. There is something in the building code that does say you have to have a primary heat source, right? You cannot just rely on that particular one. Now that again is subject to where you are climatically in the zones, but that's something again, Claude, that you'd have to also consider if you're thinking about replacing your furnace with a split heat pump. you're going to have a secondary heat source like an electric baseboard, or again, like gas. Wood doesn't count because if you leave your home, you can't stop, keep that running, right? So that is a requirement in part 4, I believe, of the building code, right? It's just a point I'd like to bring up.
Okay, great conversation again.
Yeah.
Likewise, Trevor, well done. We have information which we will be posting to follow up on some of our net zero work in the Arctic, and that should get up probably Claude, next week, we hope.
I'm working away on it right now.
Oh, there you go. All right, next hour. God, he's good. Yeah, so this is part and parcel of a project that we received funds from NRCan to develop almost like a guide for the Arctic, the North, how to achieve net zero. We changed the parameters to how to actually achieve a high performing home. As we found in our research, many First Nations are not necessarily, especially in the Arctic, aren't necessarily concerned about net zero. They're more concerned just building a house. So we had to change the terminology and the language to say, well, if you're building, at least build to a high performance home. And so this is a series that we put together and including discussions on heat pumps. So thank you for that. Okay, I think there's any more comments or, we're always available to follow up. And if not,
Hey,
thank you.
Next week, another webinar.
Yes, right. Look forward to that. All right. Thank you, everyone. Enjoy your day.
Thanks. Have a great day.
Take care.
Thanks.
Thanks,
Bye-bye.
everyone. Have a great day.
Thank you. Thank you. Thank you,
Bye.
Trevor.
You're welcome. Take care.